Hey guys, welcome back to our second day in our thermochemistry unit, again where we're talking about some different applications of heat. And today's lesson is all about a topic called calorimetry. And so that word may remind you of the word calories, which is something that we're quite familiar with on many of our, food labels, on Gatorade bottles, just lots of different places. And so what we're going to find out today is that calories are just really a way of measuring energy, okay? And so here's kind of the thought I want you to have is that our bodies, they maintain an internal temperature of around, 98.6 degrees Fahrenheit, give or take. And so that generation of that temperature, we have to have energy to make that happen. And so the energy that we gain comes from food, all right? Now, food is made up of lots of different molecules, and those molecules all have bonds. And so within the bonds is where that energy is stored. And so in us eating or consuming the food, those bonds are broken, and that releases energy that we can use to then do things like maintain our body temperature, to run, to laugh, to jump, all those good things. And so today what we're going to do is talk a little bit about, what a calorie is, and then go through a lab as to how they calculate the amount of calories in a piece of food. And so I'm going to start off by showing you a TED Ed video called What is a Calorie?
We hear about calories all the time. How many calories are in this cookie? How many are burned by 100 jumping jacks, or long distance running, or fidgeting? But what is a calorie really? And how many of them do we actually need? Calories are a way of keeping track of the body's energy budget. A healthy balance occurs when we put in about as much energy as we lose. If we consistently put more energy into our bodies than we burn, the excess will gradually be stored as fat in our cells and will gain weight. If we burn off more energy than we replenish, we'll lose weight. So we have to be able to measure the energy we consume and use, and we do so with a unit called the calorie. 1 calorie, the kind we measure in food, also called a large calorie, is defined as the amount of energy it would take to raise the temperature of 1 kilogram of water by 1 degree Celsius. Everything we consume has a calorie count, a measure of how much energy the item stores in its chemical bonds. The average pizza slice has 272 calories. There are about 78 in a piece of bread, and an apple has about 52. That energy is released during digestion and stored in other molecules that can be broken down to provide energy when the body needs it. It's used in 3 ways. About 10% enables digestion, about 20% fuels physical activity, and the biggest chunk, around 70%, supports the basic functions of our organs and tissues. That third usage corresponds to your basal metabolic rate, a number of calories you would need to survive if you weren't eating or moving around. Add in some physical activity and digestion, and you arrive at the official guidelines for how many calories the average person requires each day. 2,000 for women and 2,500 for men. Those estimates are based on factors like average weight, physical activity, and muscle mass. So does that mean everyone should shoot for around 2,000 calories? Not necessarily. If you're doing an energy-guzzling activity, like cycling the Tour de France, your body could use up to 9,000 calories per day. Pregnancy requires slightly more calories than usual. And elderly people typically have a slower metabolic rate. Energy is burned more gradually, so less is needed. Here's something else you should know before you start counting calories. The calorie counts on nutrition labels measure how much energy the food contains, not how much energy you can actually get out of it. Fibrous foods like celery and whole wheat take more energy to digest, so you'd actually wind up with less energy from a 100-calorie serving of celery than a 100-calorie serving of potato chips. Not to mention the fact that some foods offer nutrients like protein and vitamins, while others provide far less nutritional value. Eating too many of those foods could leave you overweight and malnourished. And even with the exact same food, different people might not get the same number of calories. Variations in things like enzyme levels, gut bacteria, and even intestine length means that every individual's ability to extract energy from food is a little different. So a calorie is a useful energy measure, but to work out exactly how many of them each of us requires, we need to factor in things like exercise, food type, and our body's ability to process energy. Good luck finding all of that on a nutrition label.
Okay, so with that in mind about what a calorie actually is, let's go into a little more depth and talk about how they actually kind of find out, well, how many calories does something have in the first place. It's like the video said, a calorie is just essentially a way to measure energy. And so the device that's going to measure how much energy is released by the food is what's called a calorimeter, all right? And so let's go over just a little bit of the design of this certain system. So a calorimeter is a box normally, and what's inside the box is a good bit of water, okay? So you have a big box with water, and what's important is that the box is really well insulated. And so what that means is you've got kind of some sort of material that's going to keep the heat inside the calorimeter instead of allowing it to be transferred outside of the box to the surroundings. Now, inside the water, there's another smaller container or box, and this is where the food item is going to go. Once the food is inside the box, it's going to be ignited. So essentially set on fire and it will start burning. Now the reason this is it's designed to simulate kind of the breakdown of the food, those breaking of the bonds that would happen in our body. You know, it's not an exact one-to-one comparison because like the video said, some foods digest a little bit differently. But essentially they're just trying to see how much energy is going to be released by breaking the food down. And so what happens once the food is set on fire, it's going to burn for a period of time. As it burns, it's going to release heat, and this little box is going to heat up. So the heat is going to travel from the food inside the box, kind of out into the water, all right? So the food is burning, it's giving off heat. As a result, the water temperature is going to start going up. And so the main measurement that you're actually going to take is the temperature of the water, and that's where the thermometer comes in. So the food releases energy that heats up the water, and we're going to measure the temperature change as a result. And so when it comes down to the calculation, this is the main assumption that it's built upon, is that the heat, and we're going to use the symbol, a lowercase q for heat, that the heat that is released by the food item, whatever that food may be, is going to be equal in amount to the heat absorbed by the water in the calorimeter. So let me write that down. So the heat released by the food is equal to the heat absorbed by the water in the calorimeter. Now, because the food is in the box, we can't measure it directly. So what we're measuring is what's related to the water. So if we expand kind of this side of our formula right quick, the heat that's absorbed by the water is equal to mc delta T. Now, each of these things are going to be specific to the water. The M is going to be the mass of water in the calorimeter. That will be measured in grams. The C is what's called the specific heat of water. And that's a term that is set that you can look up. The units for that are joules divided by a gram times a degree Celsius. Okay? And so the specific heat of water has a set value of 4.184. All right? And just real quick before we talk about the delta T, I've got one more slide for you on specific heat. And so the way specific heat is defined is it's substance dependent. So every substance has its own specific heat. So metal, wood, water. And so the specific heat of an object is the amount of energy that's required to raise the temperature of that substance by 1 degree Celsius. So to raise the temperature of 1 gram by 1 degree Celsius. And so one thing that makes metals really good for cookware and for baking things is they have a low specific heat, which means it only takes a little bit of energy to raise their temperature. However, water has a high specific heat, and so that means it takes a lot of energy to raise its temperature. And so, for example, there's a lot of water kind of at beaches, and so that's why beaches tend to keep a more constant temperature year-round, is because of water's higher specific heat. All right, so that's what the little c is. And then finally, this delta T, that stands for the change in temperature. And again, since the water is being heated up, what we expect is for the final temperature to be greater than the initial temperature. So the way we'll find that change in temperature is we'll take the final temp and subtract the initial temperature. All right, so now let's keep going. So what we're going to do is walk through kind of one example to get you ready for the lab that you'll be doing today. The example, we're going to do a potato chip, but in lab, you'll have lots more of your foods to choose from. I think they've got like broccoli, chocolate, tortillas, lots of different stuff. And so what we're going to walk through is what do you do with the data, once you collect it from this calorimetry experiment, once we burned the food and found out how much the water temperature was raised. All right, so they tell us we burn a potato chip with a mass of 0.67 grams, and they measure the change in temperature using a calorimeter with 50 grams of water. The temperature starts at 21.5 degrees Celsius and rises to 24.2 degrees Celsius. How much energy in joules was released by the potato chip? So we're going to start off with our assumption that the heat released by the chip is going to be equal to the heat absorbed by the water. And so the heat absorbed by the water, we'll be able to calculate that with mc delta T, where again, all of these components are specific to water. So for M, we need the mass of water, which was 50 grams in our calorimeter. And I think on y'all's paper it says 50.0, so let me kind of add that in there. Then C, we need the specific heat of water, which is that set value of 4.184 joules per gram times degrees Celsius. Oops, let me get my slash in the right place. And then finally, we need to calculate the change in temperature. So the change in temperature, we're going to take the final temperature and subtract the initial temperature. Our final temperature was 24.2 degrees Celsius, and our initial temperature was 21.5 degrees Celsius. And so the difference between those will tell us by how much the water was warmed. And so when you solve that out, oops, and I just accidentally added there, sorry about that. When you solve that out, you get a temperature change of 2.7 degrees Celsius. And so that's what goes in for our delta T. Then all of these variables just get multiplied together. So 50 times 4.184 times 2.7. And that gets us 564. And if we round that off, we'll go ahead and call it 565 joules. And we may think, wow, that kind of sounds like a lot. But oftentimes when we talk about food energy, we refer to it in terms of calories instead of joules. And so what we're going to do, now that we found the heat in joules, we're going to convert it into calories so we can have a little better comparison to an actual food package. All right, so here are some facts to kind of know in order to do this conversion. So about 4 joules is equal to 1 small calorie. Now, what makes us a little bit different here in the United States is for our food, on the packages, we don't use just a regular small calorie. We use what's called a large food calorie with a capital C, okay? And so our food calorie is equal to 1,000 of just normal small calories. So it's really like a kilocalorie, okay? And so what we're going to have to do is kind of set up a little conversion. So in joules, we started with 565 joules, and we want to get it all the way to big food calories. So our first step will be to use our conversion factor to go from joules to just normal small calories. So it takes 4.184 joules to equal 1 normal small calorie. Then our second step will be to go from small calories to large food calories. And so again, it takes 1,000 of those small calories to equal 1 large food calorie. So we'll go ahead and solve that out. So it'll be 565 divided by 4.184 divided by 1,000, since those are in the denominator. And what that finds us is it's 0.135 big C calories. And sometimes you'll see that abbreviated 0.135 and then CAL with a capital C again. But now here's the idea, is potato chips come in different sizes. Some end up being a little smaller than others when you get the bag. And so what we need is some sort of kind of reference point for what sort of size, potato chip does this 0.135 calories compare to. So typically, to get a good reference point, we're going to express it in calories per gram. So we know that for our potato chip, it measured 0.135 calories. And so what we need to do now is look back and find the grams of the potato chip that we burned. Now what will happen in the lab is that you're going to take the mass of the potato chip 2 times. You'll mass the chip before you burn it, and then you'll also mass the chip after you burn it when it's smaller. And the mass that you're going to use to calculate the calories per gram is the difference between your starting chip and your ending chip. Because again, that chip that was burned, and so it was the burned part that contributed to these calories, this energy given off. So our problem, if we went back and read the scenario, it told us that that amount that was burned was 0.67 grams. So what we'll do is we'll go ahead and divide 0.135 divided by 0.67 grams. And so that gets us 0.20 calories per gram for our potato chip. Now, I kind of put a little value there at the bottom for us that says the accepted calories per gram of potato chip is 5.7 calories per gram. How did our results compare? And so typically when we do this lab in the actual lab at school, our calorimeters are not very professional and they're not very well insulated whatsoever. And so a lot of the heat that should have gone into the water is actually lost to the surroundings. And so our results oftentimes end up being a lot lower in calories than what we find on the food package. But since you guys will be doing the virtual lab, hopefully your results should be a good bit better. And so right quick, let me take you to that screen and let you see what the lab will look like. And so what it will have is kind of a little lab setup where you've got a mass balance, you've got your calorimeter here, here's your little thermometer at the bottom, and you'll have several different food items you can choose from. And so we're only going to measure 3 of them, just kind of to save time. And so what you'll do is there's a Google Doc on Google Classroom that will kind of step you through how to log on to the simulation. And then once you're in the simulation, it will give you instructions kind of here in this yellow box. You'll complete the instructions, and then when you're ready to go to the next step, you'll hit this little arrow here. Now, the main thing that you'll be using to do this is your lab notebook, and it gives you a little place for predictions and also to collect your data, and that will help you fill in the Google document as you go along. All right, but I'm excited about this. I hope this will work well and give you a little better experience of how calorimetry works. But thanks so much, as always, for watching, and hope you guys have a great rest of your day.